Somewhere out there, in the black ocean of space, an object burns with the fury of 1,000,000,000,000 suns. It's so bright that if you placed it where our sun sits, its light would vaporize every planet in our solar system within hours. And yet, this isn't a star, it's something far stranger. This is a quasar, one of the most violent, mysterious, and mind-bending phenomena in the universe. For decades, these cosmic monsters have baffled astronomers, defying the laws of physics as we know them. They're not just distant curiosities, they're the universe's way of showing us how little we truly understand. Imagine a lighthouse, but instead of guiding ships, its beam could pierce through galaxies, visible billions of light years away. That's the power of an active galactic nucleus, or AN, the engine at the heart of a quasar. These objects aren't just bright, they're cosmic enigmas capable of warping space-time, spitting out jets of superheated plasma longer than entire galaxies, and even hiding supermassive black holes millions of times heavier than our sun. Just how do they work? Why do they behave in ways that seem to break every rule? And what can these bizarre phenomena teach us about the birth and death of the universe itself? Today, we're diving deep into the unknown to uncover 25 of the most astonishing, unsettling, and downright bizarre facts about quasars and AGNs. From their ability to outshine entire galaxies to the eerie whispers of radiation they leave behind, these cosmic anomalies challenge everything we thought we knew. Some of what we'll explore might sound like science fiction, black holes acting like cosmic fountains, beams of energy that twist reality itself, even clues that quasars could be the key to understanding dark matter. But this isn't fiction, it's the cutting edge of astrophysics, and by the end you'll see the universe in a whole new light. So strap in, we're about to journey to the edge of space and time. At the heart of every quasar lies a monster, a supermassive black hole so dense, so powerful, it warps the very fabric of space around it. But here's the twist, it's not the black hole itself that creates the blinding light we see. It's the chaotic, violent dance of matter being ripped apart just outside its grasp. Picture a cosmic whirlpool where gas, dust, and even entire stars spiral inward at nearly the speed of light, superheated to millions of degrees. This swirling vortex, the accretion disk, glows brighter than anything else in the universe, an inferno so intense it can outshine 1,000 galaxies combined. What makes this even more mind-blowing is the sheer efficiency of this process. A quasar converts matter into energy with terrifying precision, releasing up to 40% of the mass's energy as light. Compare that to the nuclear fusion in stars, which ekes out less than 1%. It's like the difference between a candle and a supernova, and yet the whole spectacle happens in a space no larger than our solar system. Imagine squeezing the brightness of 1,000,000,000,000 suns into a speck so small, our telescopes struggle to see it as anything more than a single, brilliant point in the sky. But how does something so compact produce so much power? The secret lies in the black hole's gravitational grip. As material falls in, friction within the accretion disk turns it into a seething plasma, emitting X-rays, gamma rays, and jets of particles shot into space at nearly light speed. These jets can stretch for millions of light years, punching through galaxies like cosmic blowtorches. It's a level of violence we can barely fathom. A single quasar, fueled by a black hole billions of times heavier than our sun, rewriting the rules of energy production in the cosmos. If the accretion disk is the quasar's furious heart, then its relativistic jets are the cosmic scream tearing through the silence of space. Picture this, twin beams of supercharged plasma, hotter than the core of a star, blasting outward at 99.9% the speed of light. These aren't gentle streams, they're intergalactic railguns, firing particles with so much energy they can punch through entire galaxy clusters without slowing down. And they don't just fade quietly into the void. Over millions of years, these jets slam into the sparse gas between galaxies, creating shock waves that carve out colossal cavities, structures so vast they're called radio lobes, glowing like ghostly halos in the deep radio spectrum. What's truly unsettling is how these jets defy intuition. You'd expect matter spewing from a black hole to spray chaotically in all directions, like water from a broken pipe. Instead, quasars focus their energy into laser-straight beams, tighter than anything we could engineer. The secret, magnetic fields trillions of times stronger than Earth's, wound into corkscrews by the black hole's spin. These fields act like particle accelerators, funneling the plasma into narrow columns with terrifying precision. One theory suggests the jets might even twist space-time around them, creating a vortex that keeps the beam unnaturally straight across millions of light years. The aftermath is even more dramatic. When these jets collide with intergalactic gas, they don't just dissipate, they trigger chain reactions. The impact zones glow with X-rays and gamma rays, while the displaced gas cools into new galaxies over eons. It's a cosmic feedback loop, quasars reshaping the very environments that birthed them. Some astronomers believe these jets could be the universe's way of regulating star formation, like a cosmic thermostat. Too much gas in a galaxy cluster, a quasar fires up, blasts it away, and prevents runaway stellar births. The universe, it seems, has its own violent methods of keeping balance. But here's the twist: sometimes these jets don't stay straight. A few quasars produce corkscrewing jets that wobble like spinning tops, carving helical scars through space. Others flicker on and off over millennia, leaving behind disconnected bubbles of radio emission like breadcrumbs in the dark. And in rare cases, the jets bend sharply, as if hitting some invisible wall. The leading theory: they're colliding with dark matter filaments, the hidden scaffolding of the cosmos. If true, these misbehaving jets might be our best clue yet to mapping the universe's invisible skeleton. The scale is almost incomprehensible. A single jet from a distant quasar can stretch 50 times the length of our Milky Way, yet its source is smaller than Pluto's orbit around the Sun. That's the paradox of quasars' unimaginable power packed into a speck of space, echoing across the cosmos for billions of years. These aren't just fireworks, they're the universe's way of scribbling its secrets in radiation across the sky, waiting for us to decipher them. One of the strangest quirks of quasars isn't just their unbelievable brightness, it's how that brightness can change in the blink of a cosmic eye. Picture an object trillions of miles across with the mass of billions of suns flickering like a candle in the wind. Some quasars swing wildly in brightness over mere days or weeks, a behavior so baffling it forces us to rethink everything we thought we knew about their structure. If something that big dims and reignites that quickly, conventional physics says it shouldn't even be possible. The speed of light alone should mean changes take years to propagate across its full diameter. So what's really going on? The leading suspect is the accretion disk itself, that maelstrom of superheated gas spiraling into the black hole. Under normal conditions, we'd expect changes in brightness to happen gradually, smoothed out by the sheer scale of the disk. But quasars don't play by normal rules. Instead, their disks might be riddled with violent instabilities, regions where magnetic fields snap like rubber bands, or where gas clumps into dense knots before shattering. Imagine a pot of water boiling over. Most of the time, bubbles rise evenly, but sometimes a pocket of steam explodes violently to the surface. Now scale that up to a cosmic catastrophe, where these explosions unleash enough energy to outshine galaxies. Some astronomers propose an even wilder idea. What if we're not seeing the whole disk at all? Gravitational lensing from the black hole could magnify tiny, ultra-bright regions near the event horizon, making them appear as the quasar's primary light source. If those hotspots flicker, say, from collisions between gas streams or sudden magnetic reconnection, the entire quasar's brightness might seem to fluctuate overnight. It's like watching a strobe light in a foggy room. The fog diffuses the light but doesn't hide its rapid pulses. Then there's the rogue theory. Maybe some quasars harbor not one, but two supermassive black holes locked in a gravitational dance. As they orbit each other, their competing gravitational tugs could stir the accretion disk into frenzy, creating chaotic bright spots that wax and wane unpredictably. Binary black holes would also explain another oddity: quasars with periodic brightness dips, as if something is passing in front of the light source on a cosmic schedule. Whatever the cause, these flickers aren't just academic curiosities. They're clues written in light, hinting at processes we've never witnessed firsthand. By studying the tempo of a quasar's heartbeat, astronomers can reverse engineer the hidden physics of the most extreme environments in existence. Every flicker carries a message, an echo of the chaos churning just beyond the event horizon's edge. If you thought quasars were just bright, wait until you hear how fast they're running away from us literally. The light from these cosmic beacons doesn't just travel across space, it arrives stretched, reddened, as if the universe itself is tugging at its wavelengths like taffy. This phenomenon, called redshift, isn't just a quirk. It's a screaming clue that quasars aren't just distant, they're some of the farthest objects we've ever detected, racing away from us at speeds approaching the cosmic speed limit. The numbers are staggering. Some quasars exhibit redshifts so extreme, their light has traveled for over 13 billion years to reach us, meaning we're seeing them as they were when the universe was barely out of its infancy. But redshift isn't just a measure of distance, it's a time machine. When we observe a quasar with a high redshift, we're not just seeing an object far away, we're glimpsing the universe in its turbulent youth. The light from these quasars left its source when galaxies were still forming, when the cosmos was a chaotic soup of hot gas and nascent stars. By studying their spectra, the unique fingerprints of elements in their light, astronomers have found something shocking. Even back then, the universe was already cooking up heavy elements like carbon and iron. That shouldn't be possible so early in cosmic history unless stars were forming and dying at breakneck speeds, seeding the cosmos with the building blocks of planets and life far sooner than anyone predicted. Here's where it gets even weirder. Quasar redshifts don't just tell us about the past, they're testing the fundamental laws of the universe's expansion. According to Einstein's theory, space itself is stretching, carrying galaxies and quasars along for the ride. But some quasars seem to defy expectations, clustering in ways that challenge our models of dark energy, the mysterious force accelerating cosmic expansion. Are these outliers flukes, or could they hint at something deeper, like undiscovered physics or even flaws in our understanding of gravity itself? Then there's the puzzle of redshift deserts, strange gaps in the quasar population at certain distances. It's as if the universe hit pause on quasar formation for hundreds of millions of years. One theory suggests these deserts mark epochs when supermassive black holes temporarily starved, their fuel cut off by galactic collisions or changes in the cosmic environment. Others propose that the light from these missing quasars was absorbed by vast clouds of primordial hydrogen, leaving eerie silences in the data. Whatever the cause, these gaps are like cosmic breadcrumbs, leading us toward answers about how black holes and galaxies grew up together. The most mind-bending implication: quasar redshifts might be hiding clues about the universe's ultimate fate. By comparing quasars at different distances, and thus different eras, scientists can measure whether the rate of cosmic expansion has changed over time. Early results suggest dark energy's grip might be tightening, hinting at a future where the universe doesn't just expand but tears itself apart atom by atom. If true, quasars aren't just relics of the past, they're prophets of the cosmos's end. Every flicker of their redshifted light is a piece of a puzzle we're only beginning to assemble, a code written in the stretching of space-time itself. Quasars don't just light up the cosmos, they reshape it, carving out eerie voids where star formation grinds to a halt. These are the so-called dead zones, vast regions around quasars where galaxies should be bustling with newborn stars, but instead they're eerily silent. The culprit, a brutal 1-2 punch of radiation and cosmic winds. Picture a hurricane of high-energy particles screaming outward from the quasar's core, scouring gas clouds clean before they can collapse into stars. It's like holding a blowtorch to a snowstorm. The raw energy evaporates the very ingredients needed for stellar birth. But here's the paradox: in other corners of the universe, quasars seem to do the exact opposite. Some galaxies hosting these violent engines are stellar nurseries on overdrive, churning out stars at rates that defy logic. How can the same phenomenon both stifle and spark star formation? The answer lies in the delicate balance between destruction and creation. When a quasar's jets plow into a galaxy's gas reserves, they don't always obliterate it, sometimes they compress it. Think of it like squeezing a balloon. Apply just the right pressure and pockets of gas collapse under their own weight, igniting star formation in their wake. It's cosmic alchemy, turning chaos into new life. The dead zones, though, tell a darker story. Telescopes have spotted galaxies near quasars where star birth isn't just slowed, it's snuffed out entirely. The quasar's radiation strips electrons from atoms, ionizing gas to the point where it can't cool down and clump together. Meanwhile, its outflows act like interstellar bulldozers, shoving star-forming material into the void. The result, a galactic ghost town where the streets are littered with the remains of gas clouds that never got to shine. What's truly bizarre is how selective this process seems. Some galaxies withstand the quasar's assault and emerge with even more stars, while others are left barren. Astronomers suspect it comes down to timing and geometry. A quasar firing its jets directly into a galaxy's gas-rich core can sterilize it in a cosmic instant. But if those jets hit at an angle, or if the galaxy is already packed with dense gas, the shockwaves might trigger a starburst instead. It's a reminder that in the universe, even destruction can be a creative force. The dead zones also hold clues about one of astronomy's biggest mysteries: why the universe's star formation rate peaked billions of years ago and then declined. Quasars, it seems, might be the universe's ultimate regulators, flipping the switch on stellar birth when galaxies grow too crowded. By studying these silent patches, we're piecing together a story of cosmic feedback, one where the brightest objects in existence also cast the longest shadows. Deep in the cosmic archives, astronomers have stumbled upon something that shouldn't exist: two quasars side by side, locked in a gravitational tango. These aren't just random neighbors, they're binary quasars, rare systems where two supermassive black holes, each powering its own luminous beacon, orbit one another in a slow-motion dance that could last millions of years. The odds of spotting such a pair are astronomically low. Quasars themselves are already fleeting phenomena, active for just a blink in cosmic time. So finding two that are not only active simultaneously but close enough to interact. It's like stumbling upon twin lightning strikes hitting the same grain of sand. What makes these duos so special isn't just their rarity, it's what they reveal about the violent mergers that shape galaxies. When two galaxies collide, their central black holes eventually sink toward each other, drawn by gravity. But instead of merging immediately, they can spiral inward for eons, whipping up chaos in their wake. Gas and dust funneled toward this pair of black holes ignite both as quasars, creating a double beacon visible across the universe. The energy output is unimaginable: two accretion disks blazing side by side, their light flickering in sync as they orbit. Yet spotting these pairs is like trying to distinguish two fireflies from a mile away. Even with the most advanced telescopes, binary quasars often appear as a single point of light. Confirming their true nature requires painstaking analysis of their spectra, looking for subtle shifts in wavelength that betray the Doppler effect as one quasar moves toward us while the other recedes. Only a handful have been confirmed so far, each one a treasure trove of data. The real fireworks begin when these black holes finally merge. As they inch closer, their orbit tightens, and they begin rippling space-time itself, sending out gravitational waves, echoes of the collision that propagate across the cosmos. These waves carry energy equivalent to millions of supernovae, but they're so faint by the time they reach us that only instruments like LIGO and future space-based detectors could hope to catch them. The merger of supermassive black holes would produce waves with frequencies too low for current technology, a deep, cosmic hum lost in the noise of the universe. Why does this matter? Binary quasars are snapshots of a fleeting phase in galactic evolution, a preview of the Milky Way's own fate when it collides with Andromeda billions of years from now. They're also natural laboratories for testing Einstein's general relativity under extreme conditions. The way their orbits decay over time could reveal secrets about how black holes interact with their surroundings, whether they plow through gas like bullies or glide smoothly like figure skaters. But the most tantalizing possibility is that these systems might solve a long-standing mystery: how supermassive black holes grow so big so fast. If binary quasars are more common than we thought, their mergers could be the universe's shortcut for building behemoths. Every collision would funnel fresh material into the surviving black hole, bulking it up in a cosmic feeding frenzy. Some theorists even speculate that the recoil from particularly violent mergers could kick the newly formed black hole clean out of its galaxy, sending it careening into intergalactic space as a dark, homeless wanderer. For now, every binary quasar discovered feels like uncovering a Rosetta Stone for black hole evolution. Each one is a puzzle piece in the grand mosaic of how galaxies and the universe itself grew up. And with new telescopes like the Vera Rubin Observatory coming online, we might soon find that these cosmic duets aren't as rare as we once believed. The universe, it seems, has a flair for drama, and nothing is more dramatic than two quasars spinning toward an inevitable, earth-shattering embrace. Quasar light echoes are the universe's way of keeping secrets, but not forever. Imagine turning off a flashlight in a pitch-black cave, only to watch its beam continue to bounce off the walls long after the source has vanished. That's what happens when a quasar flares up and then dims, its light still traveling outward, illuminating cosmic gas clouds like a ghostly afterglow. These echoes aren't just pretty relics, they're time capsules, preserving snapshots of a quasar's violent outbursts from millions of years earlier. The mechanics are both simple and mind-bending. Light from a quasar's eruption races through space until it slams into a distant cloud of gas. Some of that light gets absorbed, but the rest scatters in all directions, including back toward us. By the time these scattered photons reach Earth, the quasar itself may have faded to a whisper, but the echo lingers, carrying a message from its fiery past. Astronomers call this phenomenon light echoes, and they're like cosmic detective work. By analyzing the spectrum of these delayed glows, scientists can reconstruct what the quasar was doing centuries or even millennia before we observed it directly. It's as if the universe left us a voicemail and we're just now hitting play. One of the most stunning examples lies in the neighborhood of a quasar called Markarian 231. In 2012, researchers noticed faint wisps of ultraviolet light radiating from gas clouds hundreds of light years away, light that matched the quasar's signature but arrived decades late. The conclusion: Markarian 231 must have undergone a cataclysmic flare-up in the early 20th century, a burst of energy so powerful it still lights up the surrounding cosmos like a fading firework. Without the echo, we'd have no idea the quasar ever behaved that way. But the real magic happens when these echoes reveal repeated outbursts. Some quasars show multiple layers of illuminated gas, each corresponding to a different eruption in the past. It's like finding tree rings in space. Each bright shell tells a story of another violent chapter in the quasar's life. One study even found evidence of a quasar pulsing every few thousand years, as if something perhaps a second black hole in a tight orbit, was periodically dumping fresh fuel into the accretion disk. Light echoes also solve a cosmic riddle: how quasars shut off. Conventional wisdom says these objects fade slowly as they exhaust their fuel. But echoes suggest some quasars don't go quietly. They flicker wildly before vanishing, like a candle sputtering in the wind. In some cases, the echoes show abrupt drops in brightness, hinting that the quasar's feeding frenzy was cut short by a galactic collision or a sudden shortage of gas. It's a reminder that even the universe's most powerful engines are at the mercy of their surroundings. The most profound implication: these echoes let us study quasars in 4D, not just their current state, but their entire life cycle. A single echo can reveal how a quasar's energy output changed over centuries, how its jets wobbled, or even how its black hole grew. In a way, we're not just observing these objects, we're rewinding time, watching their histories unfold in reverse. And with new telescopes like the James Webb Space Telescope peering deeper into the infrared, where echoes often hide, we're on the verge of uncovering even more of these cosmic palimpsests, each one a scribble in the margins of the universe's grand story. Quasars aren't just cosmic lighthouses, they're also the universe's ultimate flashlights, illuminating secrets hidden in the darkness between galaxies. When their piercing light travels across billions of light years, it doesn't arrive untouched. Along the way, it passes through vast clouds of gas, each one leaving behind a fingerprint in the quasar's spectrum. These fingerprints, called absorption lines, are like barcodes etched into the light, revealing the composition, temperature, and even the motion of material we'd never see otherwise. It's as if quasars hand us a key to decode the invisible scaffolding of the cosmos. One of the most fascinating patterns in these absorption lines is known as the Lyman alpha forest, a whimsical name for something profoundly revealing. When quasar light encounters clouds of neutral hydrogen, the gas absorbs specific wavelengths, creating a series of dark lines in the spectrum. But because the universe is expanding, each cloud lies at a slightly different distance, stretching these absorption lines into a dense thicket of trees in the data. The result, a forest of lines, each representing a separate hydrogen cloud along the line of sight. The denser the forest, the more structure exists in the universe's primordial gas. But the Lyman alpha forest isn't just a cosmic census of hydrogen, it's a time capsule. The closer the absorption lines are to the quasar's own redshift, the younger the universe was when that gas got in the way. By studying these forests in quasars at different distances, astronomers have mapped how the universe evolved from a smooth sea of gas into the web-like structure we see today. Some of these clouds are leftovers from the Big Bang, pristine pockets of hydrogen untouched by stars. Others bear traces of heavier elements, evidence that supernova had already begun polluting the cosmos with the raw materials for planets and life billions of years ago. Here's where it gets even wilder. The spacing between the trees in the Lyman alpha forest tells us about the temperature and clumpiness of the early universe. Tightly packed lines suggest a cooler, denser environment, while sparse ones hint at regions heated by the first galaxies or quasars. In some cases, the forest even reveals vast bubbles, regions where quasar radiation ionized the surrounding hydrogen, clearing it out like a cosmic blowtorch. These bubbles are the footprints of the universe's first epoch of reionization, when light finally broke free from the fog of the early cosmos, the most astonishing part. This technique doesn't just work for hydrogen. Heavy elements like carbon, oxygen, and silicon also leave absorption lines, betraying the presence of gas enriched by generations of stars. Some quasars shine through galaxies too faint to see directly, but their absorption lines give them away, like spotting a hidden object by its shadow. In one famous case, a quasar's spectrum revealed a galaxy made almost entirely of dark matter, its sparse gas the only visible clue to its existence. Quasars, it turns out, are more than just brilliant objects, they're the ultimate cosmic probes. With every absorption line, they sketch a map of the universe's hidden anatomy, tracing the rivers of gas that flow between galaxies and the echoes of the first stars. And as our telescopes grow sharper, these backlit revelations promise to expose even deeper secrets, like the nature of dark matter or the birthplaces of the very first black holes. The universe wrote its history in gas and light, and quasars are helping us read it one absorption line at a time. Just when astronomers thought they had quasars figured out, the universe threw them another curvable objects that shape-shift right before our eyes. Meet the changing-look quasars, cosmic chameleons that can transform from dazzling beacons to faint shadows in just a few years. One moment, they're classic Type 1 quasars, blazing cores visible through thin veils of dust. The next, they've morphed into Type 2 quasars, their light smothered, as if someone flipped a cosmic dimmer switch. These aren't subtle shifts. Some quasars have dropped in brightness by a factor of 50, vanishing from plain sight. The question keeping scientists up at night: is this a celestial magic trick, or are we witnessing the raw, chaotic heartbeat of a black hole's appetite? The leading theory points to dust, lots of it. Imagine a supermassive black hole's feeding frenzy, surrounded by a swirling, clumpy storm of cosmic soot. If a particularly thick dust cloud drifts across our line of sight, it could blot out the quasar's accretion disk, turning a Type 1 into a Type 2 overnight. But that's the boring explanation, and the universe rarely sticks to boring. Observations show some changing-look quasars alter their entire spectra, not just their brightness. The broad emission lines characteristic of Type 1 quasars vanish, suggesting something far stranger than a passing dust cloud. The black hole's inner sanctum, it seems, is undergoing a radical transformation. That's where the second theory comes in. What if the black hole itself is choking? Quasars shine because material spirals into them, but that flow isn't always steady. A passing star torn apart by tidal forces might flood the accretion disk with fresh fuel, causing a bright outburst. Later, when the snack runs out, the disk could sputter and fade. In this scenario, changing-look quasars aren't being obscured, they're literally running on empty. Supporting this idea, some quasars show correlated changes in both their visible light and X-ray emissions, something dust alone can't explain. It's like watching a car's engine stall. The lights dim because the power source is faltering, not because someone draped a blanket over the headlights. The plot thickens with rare cases where quasars flip-flop multiple times. Take the case of J1012 plus 0643, a quasar that switched classes at least twice in the past 2 decades. If dust were the culprit, we'd need an unlikely cosmic ballet of clouds drifting in and out of view with clockwork precision. Instead, some researchers suspect binary black holes might be at play, 2 monsters orbiting each other, alternately feeding and fasting as their gravitational dance stirs the surrounding gas. Every time one black hole steals the lion's share of material, its quasar ignites while the other temporarily goes dark. Changing-look quasars force us to confront how little we know about the daily lives of supermassive black holes. We tend to picture them as steady, insatiable beasts, but these transformations reveal them as dynamic, even capricious. They might spend millennia in hibernation, then wake up in a violent burst of glory, only to nod off again centuries later. And with new sky surveys scanning millions of galaxies nightly, we're finding these cosmic werewolves are far more common than anyone guessed. Each one is a lesson. The universe doesn't do monotony. Even the mightiest objects in existence have their off days and their comebacks. Sometimes quasars don't just burn with impossible brilliance, they multiply. Across the cosmos, these luminous beacons split into duplicates, not because they've cloned themselves, but because the fabric of space itself has twisted their light into cosmic mirages. This illusion, called gravitational lensing, occurs when a massive object like a galaxy or a cluster warps spacetime so severely that it bends passing light like a funhouse mirror. The result, a single quasar's light can take multiple paths to reach us, creating ghostly echoes of itself scattered across the sky. Some appear as perfect Einstein rings, halos of light encircling the lensing galaxy, while others split into crosses, arcs, or even quadruple images arranged like celestial clockwork. What makes these lensed quasars more than just pretty optical tricks is what they reveal about the universe's hidden architecture. Each distorted image carries subtle clues about the mass of the galaxy bending its light. By measuring how much the quasar's light splits and stretches, astronomers can literally weigh the lensing galaxy, including its dark matter, which exerts gravity but emits no light. It's like using a quasar as a cosmic scale, revealing how much invisible mass lurks between us and the distant universe. One famous example, the double quasar QSO 957+561, was the first to prove this technique works. Two identical quasar images separated by 6 arcseconds, their light bent by an unseen galaxy in the foreground. But the real magic happens when these lensed quasars flicker. Because each light path takes a slightly different route around the lens, the images don't brighten or dim simultaneously. A flare in one image might appear weeks or even years later in its counterpart, like an echo. By timing these delays, scientists can measure the Hubble constant, the rate of the universe's expansion, with astonishing precision. It's a cosmic stopwatch where the ticks are separated by the curvature of spacetime itself. Then there are the extreme cases like SDSS J1004+4112, where the lensing galaxy is so perfectly aligned that the quasar's light forms a complete Einstein ring, a halo of fire spanning tens of thousands of light years. These rings aren't just rare, they're pristine laboratories for testing gravity. Any deviation from the perfect circle hints at unseen structure, clumps of dark matter, rogue black holes, or even flaws in Einstein's theory itself. Perhaps the most mind-bending implication is that lensed quasars might be hiding an even bigger secret, evidence of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. If one of these filaments, thinner than an atom but denser than a mountain, were to slice between us and a quasar, it could create double images with no lensing galaxy in sight. So far, no confirmed cases exist, but the hunt continues. Every ghostly quasar image is a puzzle wrapped in the fabric of spacetime, waiting to be unraveled. If quasars are the universe's lighthouses, their outflows are the hurricane force winds that reshape entire galaxies. These aren't gentle breezes, they're supersonic tempests, blasting outward at speeds exceeding 20 million miles per hour, carrying enough energy to fling a galaxy's worth of gas into the cosmic void. Picture a cosmic fire hose turned up to 11, carving through interstellar clouds like tissue paper and leaving behind sterile galactic deserts where star formation grinds to a halt. The scale is staggering. A single quasar outflow can stretch for hundreds of thousands of light years, dwarfing the galaxy that birthed it. What makes these outflows truly bizarre is their dual nature. On one hand, they're destroyers scouring galaxies clean of the raw materials needed to make new stars. Observations of galaxies like Markarian 231 show vast bubbles in their gas reservoirs, regions where the quasar's wind has literally blown a hole in the galactic ecosystem. Hydrogen that should have cooled into stellar nurseries gets superheated to millions of degrees, becoming too energetic to collapse. It's cosmic sterilization on an epic scale. Yet paradoxically, these same outflows might also be galactic midwives. When the quasar's wind slams into surrounding gas at the galaxy's outskirts, it can trigger shock waves that compress cold molecular clouds, jump-starting star formation in the very act of suppressing it elsewhere. Telescopes have spotted starburst rings in some quasar-hosting galaxies, blazing circles of newborn stars precisely where the outflow's forward momentum stalled. It's like a wrecking ball that somehow builds houses with its debris. This push-pull dynamic might explain one of astrophysics' biggest mysteries. why the most massive galaxies stopped growing stars billions of years ago. Quasars, it seems, could be the universe's self-regulating valves, shutting off star production before galaxies balloon to unsustainable sizes. The physics behind these outflows is even wilder than their effects. Unlike stellar winds, which push material through simple radiation pressure, quasar outflows harness relativistic particle beams and tangled magnetic fields. Some models suggest the black hole's spin acts like a cosmic particle accelerator, flinging ionized gas outward along magnetic field lines that coil like DNA strands. Other theories propose that the outflow's initial kick comes from the intense radiation pressure of the quasar's accretion disk photons so energetic they literally knock electrons clean off atoms, creating a plasma wave that rips through the galaxy. Whatever the mechanism, the result is a self-perpetuating chain reaction. As gas gets expelled, the quasar's radiation penetrates deeper into the galaxy, ionizing more fuel and driving even stronger outflows. These phenomena aren't just theoretical, we've caught them in the act. The quasar known as SDSS-J1106+0199 boasts an outflow so powerful, it's ejecting 400 solar masses of material every year. That's the equivalent of tossing an entire sun-sized star into intergalactic space every 3 days. Even more extreme is APM 08279+5255, whose outflow reaches a mind-numbing 40% of light speed, fast enough to cross the solar system in under a day. At those velocities, the gas doesn't just leave the galaxy. It escapes the galaxy cluster entirely, seeding the intergalactic medium with heavy elements forged in stellar furnaces. The implications ripple across cosmology. Without quasar outflows, galaxies might have grown far larger than we observe, their star formation unchecked. The feedback problem, how galaxies self-regulate their growth, finds a compelling solution in these cosmic winds. They might even explain why supermassive black holes and their host galaxies appear to grow in lockstep. As the black hole feeds and powers its quasar, the resulting outflow shuts down the galaxy's star formation, effectively putting a cap on both systems' growth. It's a delicate dance of destruction and creation, written in the language of million-degree winds and extinguished stellar nurseries. The universe, it seems, has its own violent way of keeping balance. Some quasars defy the rules by existing where they shouldn't, floating in the cosmic void like ghost ships with no galaxy in sight. These orphan quasars challenge everything we thought we knew about how supermassive black holes form. After all, black holes this colossal, weighing billions of suns, should be anchored to galaxies, their growth fed by the surrounding gas and stars. So how do we explain quasars that appear to have no home? One possibility is that their host galaxies aren't missing, they're just invisible. Quasars are so dazzling they can outshine their host galaxies by a factor of 1,000, drowning them in glare. Think of trying to spot a candle next to a spotlight. Advanced telescopes like the James Webb Space Telescope have peeled back the glare in some cases, revealing faint, smeared galaxies hidden beneath the quasar's brilliance. These could be remnants of galactic collisions, where the chaos of merging triggered the quasar's awakening while tearing the host galaxy into a diffuse, barely detectable haze. But the plot thickens with quasars like He 0450-2958, a case so extreme it's nicknamed the homeless quasar. Even after meticulous searches, no host galaxy has been found, not even a wisp. Here, astronomers suspect something far more violent. The quasar might have annihilated its own home. The relentless radiation and supersonic outflows from these objects can strip a galaxy of its gas, halting star formation and leaving behind only a skeletal frame of old stars too dim to detect. It's cosmic fratricide, the quasar, in its hunger, devouring the very galaxy that birthed it. Then there's the rogue theory. Could some of these orphan quasars be supermassive black holes ejected from their galaxies entirely? Simulations show that when two galaxies merge, their central black holes can slingshot each other away during a gravitational tug-of-war. If a black hole gets kicked out while still surrounded by a swirling disk of gas, it could shine briefly as a quasar, a nomad blazing through intergalactic space. We might be seeing these black holes in their final act of defiance, lighting up one last time before their fuel runs out and they fade into darkness. The most tantalizing clue comes from quasars in the early universe. Some appear in regions so empty they challenge models of how structure formed. One explanation: they could be remnants of direct collapse black holes, hypothetical monsters born not from stars, but from the instantaneous collapse of primordial gas clouds in the universe's infancy. If such objects exist, they'd start life as supermassive from day one. No galaxy required floating like cosmic dragons in the void. Whether hidden, destroyed, or truly alone, these orphan quasars force us to rethink the bond between black holes and their galaxies. They're cosmic riddles written in light, asking us, how well do we really understand the universe's most powerful engines? And if some black holes can wander freely, what else might be lurking in the darkness between galaxies? Quasars may blaze with unimaginable fury, but even the brightest flames eventually burn out. Scattered across the cosmos lie their skeletal remains, supermassive black holes now sitting in eerie silence, their surroundings forever scarred by ancient outbursts. These are quasar fossils, and they tell a story not of death but of transformation. Take the galaxy MS0735+7421 for instance. At first glance, it's just another elliptical galaxy until telescopes reveal vast bubbles of radio emission stretching hundreds of thousands of light years from its core. These ghostly structures are the aftermath of jets that vanished millions of years ago, like tire tracks frozen in cosmic mud. What makes these relics so valuable is how they preserve the quasar's life story long after its light fades. When a quasar shuts down, its jets don't just vanish. They leave behind cavities in the surrounding gas, filled with magnetized plasma that continues to glow faintly in radio waves. By studying the size and shape of these cavities, astronomers can reconstruct the quasar's power and duration, like paleontologists measuring dinosaur footprints to estimate the creature's speed. Some fossils, like those around the black hole in galaxy cluster MS0735, reveal multiple layers of bubbles, evidence of episodic outbursts separated by millions of years of quiet. It's as if the black hole hibernated between meals, waking occasionally to unleash another cataclysm. The most revealing fossils, though, are those caught mid-transition. Objects like NGC 5128's central black hole show jets that sputter intermittently, alternating between states of activity and dormancy. These zombie quasars demonstrate that shutdown isn't always permanent. Black holes can reawaken if fresh gas drifts too close. Their surroundings often bear the scars of both past and present activity, with old radio lobes overlaid by newborn jets. It's a cosmic palimpsest, with each eruption writing over the last. Then there's the case of galaxy cluster HLX1, home to one of the most puzzling fossils yet. Here, X-ray observations show a pair of cavities, each large enough to swallow the Milky Way, but no visible black hole activity. The leading theory: the central black hole feasted so violently in the past that it blasted away all nearby gas, starving itself into quiescence. Now it sits in darkness, surrounded by the echoes of its own gluttony. Quasar fossils also hold clues to one of astrophysics' biggest mysteries: why the universe's quasar population peaked 10 billion years ago and then declined. The answer might lie in these relics. As galaxies aged, mergers became rarer, cutting off the gas supply that once fed their central black holes. Without fresh fuel, quasars dimmed, leaving behind fossils as tombstones to an earlier, more violent era. Yet some, like the black hole in galaxy M87, remind us that dormancy isn't forever. Given enough time and the right cosmic buffet, even the quietest giants can roar back to life. Among the most baffling discoveries about quasars is a pattern so vast it defies explanation: their rotation axes, the invisible lines around which their accretion disks spin, appear eerily aligned across distances spanning billions of light years. It's as if these cosmic engines, separated by voids so immense light takes eons to cross them, are somehow choreographed by an unseen hand. The odds of this happening randomly are astronomically slim, like flipping 1,000,000 coins and having every single one land heads up. Could this alignment be a fluke, or is it evidence of something far stranger? A hidden cosmic scaffold woven from dark matter. The first clues emerged when astronomers mapped the polarization of light from over 100 quasars. Polarization, the direction light waves vibrate, often reflects the orientation of a quasar's accretion disk. To the researchers' shock, many of these disks seem to spin along parallel axes, even for quasars separated by nearly half the observable universe. The statistical probability of such alignment happening by chance, less than 1%. This isn't just a quirk, it's a cosmic mystery begging for an explanation. Dark matter, the invisible glue holding galaxies together, might hold the key. Simulations suggest that dark matter doesn't just clump randomly, it forms vast filaments, a web-like structure stretching across the cosmos. Galaxies, and by extension their central black holes, form along these threads like beads on a string. If quasars are born within the same colossal filament, their spin axes could inherit alignment from the dark matter's gravitational flow, like compass needles all pointing north. The catch: these filaments would need to be unimaginably large, structuring matter across scales we've never before observed, but skeptics aren't convinced. Some argue that selection bias could be at play. Perhaps astronomers inadvertently studied quasars already linked by larger-scale structures. Others propose that the alignment is temporary, a fleeting snapshot of a dynamic universe where quasars eventually tumble into randomness. Then there's the wild card: primordial magnetic fields. If the early universe was laced with powerful magnetic fields, they might have imprinted a preferred spin direction on emerging black holes, leaving behind this ghostly synchrony. The implications ripple beyond quasars. If dark matter's tendrils truly govern black hole spins, it would mean the invisible web shapes not just where galaxies form, but how they behave. It's a radical idea: dark matter as cosmic puppet master, pulling strings we can't even see. Until we unravel this enigma, the aligned quasars remain either the universe's most elaborate coincidence or the first hint of a hidden architecture far grander than we ever imagined. Quasars serve as the universe's ultimate time capsules, their light carrying pristine messages from an era when galaxies were just beginning to assemble. The beams we observe today embarked on their journey billions of years ago, traversing vast cosmic deserts untouched by the pollution of later stellar generations. Within their spectra, those intricate barcodes of absorbed and emitted light, lies a forensic record of the early universe's chemical composition. It's like finding a perfectly preserved vial of ancient air, revealing what the cosmos breathed long before Earth even existed. What makes these spectral fingerprints so astonishing is the presence of heavy elements: carbon, oxygen, even iron detected in quasars shining when the universe was barely a tenth of its current age. These elements shouldn't have been there so soon after the Big Bang. The early cosmos was a sterile place, dominated by hydrogen and helium forged in the first 3 minutes of existence. Heavy elements only emerge from the furnaces of stars, cooked through nuclear fusion and scattered by supernova. Yet quasar spectra show these metals were already abundant, meaning stars must have lived, died, and enriched the universe with startling speed. Some quasars reveal enough iron to suggest multiple generations of stars had already flared and faded, all within the first billion years. It's as if the universe went from infancy to industrial revolution in a cosmic blink. The implications rewrite our timeline of cosmic evolution. Traditional models assumed it took eons for galaxies to produce enough stars to seed space with heavy elements. Quasars prove otherwise. Their spectra show pockets of the early universe were already as chemically rich as today's interstellar clouds. One particularly ancient quasar, J034-6836, displays iron levels nearly matching our Sun's despite existing when the universe was only 700 million years old. That's like finding a modern factory in the Stone Age. How did this happen? The leading theory points to an early population of colossal, short-lived stars, behemoths hundreds of times heavier than our Sun. These monsters would have burned ferociously and died young, exploding as supernova that peppered space with heavy elements far sooner than smaller stars could. Quasar spectra even hint at these pioneers, unusual ratios of elements like nitrogen and carbon that only make sense if they came from gargantuan stellar births. But the real magic lies in the details. Each absorption line in a quasar's spectrum acts like a time-stamped shipping manifest, listing which elements were present and in what quantities at specific epochs. By comparing quasars of different ages, astronomers have reconstructed the universe's chemical growth spurt. The youngest quasars show barely a whisper of metals, while slightly older ones reveal a sudden surge, as if the cosmos had crossed a threshold where star formation went into overdrive. Perhaps the most tantalizing clue comes from deuterium, a rare isotope of hydrogen. Quasar spectra contain precise measurements of this cosmic relic, which was forged only minutes after the Big Bang. The amount of deuterium we see acts as a cosmic scale, weighing the total density of ordinary matter in the universe. Remarkably, it matches almost perfectly with predictions from the Big Bang model, a stunning confirmation that our understanding of the universe's birth is broadly correct. Yet even here, quasars deliver a twist. Some show slightly less deuterium than expected, hinting at unknown processes that might have destroyed some of it in the violent hearts of early galaxies. These spectral messages do more than satisfy curiosity. They anchor entire branches of cosmology. Without quasars, we'd have no way to measure how quickly the universe enriched itself or how the first stars differed from those born today. Their light is a bridge across time, carrying whispers from an epoch when the cosmos was still stitching itself together. Every new quasar discovered is another page in the universe's autobiography, written in the language of atoms and light. Deep in the cosmic archives, astronomers have stumbled upon quasars that pulse with eerie regularity, their brightness rising and falling like the steady beat of a heart. These heartbeat quasars defy the usual chaotic flickering of their kind, instead maintaining rhythms so precise they could keep time as well as any atomic clock. One of the most striking examples, OJ287, brightens and dims every 12 years like clockwork, an anomaly first dismissed as coincidence until the pattern held for over a century of observations. The universe, it seems, has its own metronome, and its tempo is written in the flicker of these cosmic giants. What could possibly choreograph such precision in an environment where chaos reigns? One leading theory points to a cosmic dance of black holes specifically, a pair of supermassive black holes locked in a tight orbital embrace. As the smaller black hole swings around its partner, it periodically plows through the accretion disk, stirring up violent waves of gas that glow brighter with each pass. Think of it like a spoon circling a mug of coffee, creating ripples that crest at predictable intervals. In this scenario, the quasar's heartbeat is the flash of light from these collisions, a celestial strobe marking each lap in a gravitational waltz. But there's a twist. Some heartbeat quasars pulse too quickly for this explanation. Objects like RJ1034+396 flicker every few hours far faster than any known black hole binary could orbit without merging. For these rapid pulsars, astronomers suspect a different mechanism, a warped, wobbling accretion disk. Picture a spinning top as it begins to slow, its axis tracing lazy circles in the air. Now imagine that top is a disk of superheated gas larger than our solar system, and the wobble is driven by the black hole's immense gravity tugging at its edges. Every time the disk's tilted edge faces Earth, we see a surge in brightness, a cosmic lighthouse effect blinking in perfect rhythm. The most tantalizing heartbeat quasars, however, defy both explanations. Take Assassin 14Ko, which erupted every 114 days for nearly 2 years before suddenly falling silent. No known orbital period or disk wobble fits this pattern. Instead, researchers propose something far more dramatic, a star trapped in a death spiral around the black hole. Each time the star swings close, the black hole's gravity strips away a layer of its gas, igniting a flare before the star retreats, only to return months later for another violent embrace. It's a grisly clock ticking with the precision of celestial cannibalism. What makes these cosmic heartbeats invaluable isn't just their strangeness, it's what they reveal about black hole physics. The timing of the pulses acts like a sonogram for the quasar's hidden structure, letting astronomers map regions too small to see directly. A 12-year pulse might trace the orbit of a secondary black hole light weeks away from its partner, while an hourly flicker could betray the spin rate of the accretion disk itself. Even failed predictions are enlightening. When a quasar's heartbeat suddenly skips or changes tempo, it hints at unseen chaos, perhaps a passing star disrupting the disk or magnetic field snapping into new configurations. Heartbeat quasars challenge our assumptions about the universe's most violent objects. We expect chaos from quasars, not rhythm. Yet these cosmic drumbeats persist across billions of years, outliving civilizations, ice ages, and even the rise and fall of galaxies. Whether they are signaling the presence of hidden black hole duos, wobbling disks, or doomed stars, one thing is clear: the universe has a flair for turning destruction into poetry, writing its most profound secrets in the language of light and time. Quasars didn't just light up the early universe, they may have helped reshape it, tearing apart the cosmic fog that shrouded existence in darkness for hundreds of millions of years. This pivotal moment, called reionization, marks when the universe's hydrogen atoms, once neutral and opaque, were stripped of their electrons, transforming space into the transparent expanse we see today. But here's the cosmic detective story. Were quasars the prime culprits, or did the first stars do most of the heavy lifting? The answer could rewrite our understanding of how the cosmos woke from its slumber. For eons after the Big Bang, the universe was a featureless sea of hydrogen gas, so dense it absorbed all light like interstellar smog. Then, around 300 million years later, something began punching holes in that fog. Traditional theory points to the first stars, hot, massive beasts that blazed to life and flooded space with ultraviolet radiation. But quasars throw a wrench into that narrative. Their UV beams were thousands of times more energetic than starlight, capable of ionizing hydrogen far beyond their immediate surroundings. Telescopes have spotted quasars from this era surrounded by vast, bubble-like regions where hydrogen was completely ionized, clearings in the cosmic forest cut by their relentless light. Yet the debate rages on. Quasars were rare compared to early stars, like lighthouses dotting an ocean versus a blanket of bioluminescent plankton. Could their sparse numbers really have contributed significantly? Some simulations suggest yes. While stars ionized their local neighborhoods, quasars' piercing beams may have tunneled through the densest gas clouds, creating channels that let starlight penetrate deeper. It's like comparing a scalpel to a hammer, both tools but with vastly different impacts. Then there's the timing problem. Quasar activity peaked after reionization was already underway, suggesting stars lit the first match. But recent discoveries of ultra-early quasars, like J1342+0928, shining when the universe was just 670 million years old, hint they may have played a bigger role than we thought. Their spectra show telltale proximity zones, patches of ionized hydrogen extending tens of thousands of light years, as if they'd been clearing space long before their light reached us. The plot thickens with the discovery of Lyman alpha blobs, enormous clouds of hydrogen glowing faintly in the early universe. These structures, some spanning hundreds of thousands of light years, appear too large and diffuse to have been ionized by stars alone. Quasars with their long-range UV artillery are prime suspects, but here's the twist: some blobs lack obvious quasar hosts, implying other forces, perhaps even decaying dark matter, might have contributed. What's at stake isn't just academic. If quasars dominated reionization, it means the universe's transparency was carved by a handful of violent anomalies rather than a chorus of stars. That would imply a lumpier, more uneven transition, with some regions ionizing far earlier than others. Star-led reionization, by contrast, suggests a smoother, more democratic process. The difference shapes how we interpret everything from galaxy formation to the cosmic microwave background. Clues hide in the shadows, literally. The residual fog of neutral hydrogen left behind during reionization casts subtle absorption lines in quasar spectra, like tree rings recording the era's progress. By studying these lines in quasars of different ages, astronomers have pieced together a timeline. Reionization began in earnest around redshift 15 and wrapped up by redshift 6. But within that window, quasars' fingerprints appear sporadically, like bursts of a chainsaw amid the steady hum of crickets. The truth likely lies in a messy collaboration. Stars may have begun the work, their collective UV light eating away at the cosmic fog like termites gnawing at wood. But quasars, with their surgical precision and raw power, could have finished the job, drilling through the toughest patches and flooding the universe with light. Together, they tore the veil not with a single hand, but with a cosmic tug of war between the many and the mighty. The echoes of that struggle linger in every quasar's glow, a reminder that even the darkest ages must eventually end. Among the countless bizarre quirks of quasars, few are as glitteringly strange as the diamond quasars, objects whose light carries the spectral fingerprints of carbon crystals, possibly even diamond dust, swirling in the hellish environment around a supermassive black hole. Picture this: trillions of microscopic diamonds, forged in the violence of an accretion disk, scattering starlight like cosmic disco balls. It sounds like science fiction, but the evidence is etched in the light of quasars like J042-0761, whose infrared spectrum bears the unmistakable dip caused by carbon crystals absorbing specific wavelengths. How could something as delicate as a diamond survive, let alone form, in one of the universe's most hostile environments? The answer lies in the extreme physics of quasar outflows. When carbon-rich gas gets blasted outward by the black hole's radiation, it can cool rapidly in the relative quiet of interstellar space, allowing carbon atoms to crystallize under intense pressure. Think of it like snow forming in the exhaust plume of a rocket. Chaos gives way to sudden, fragile order. Some models suggest these diamonds might even nucleate on pre-existing graphite particles, like frost forming on a window pane. But the real shocker is the scale. Estimates suggest some quasar outflows contain enough carbon to manufacture diamonds weighing millions of tons, far larger than any gemstone on Earth. If concentrated, these could theoretically form planet-sized crystals, though they're more likely scattered as fine dust. Still, the mental image is staggering. Galaxies strewn with diamond rain, glittering in the light of their monstrous central engines. What's even more puzzling is what these carbon-rich quasars imply about their host galaxies. Stars produce carbon as they age, so an abundance of diamond dust suggests a galaxy teeming with stellar graveyards, places where generations of stars have lived, died, and donated their ashes to the quasar's furnace. Yet some diamond quasars are astonishingly young, existing when the universe was barely 1 billion years old. That's not enough time for slow-burning stars like our Sun to contribute much carbon. Instead, astronomers speculate these systems might have been seeded by short-lived, hypermassive stars from the universe's first-generation celestial giants that lived fast, died violently, and littered space with carbon before most galaxies had even taken shape. Then there's the wild card. Could these diamonds be more than just cosmic curiosities? Laboratory studies show nanodiamonds can form in supernova remnants, suggesting they might be universal byproducts of stellar death. If quasars are indeed spraying diamonds across the cosmos, those crystals could serve as interstellar hitchhikers, ferrying complex carbon compounds to newborn planetary systems. Some scientists even speculate that probiotic molecules, the building blocks of life, might form more readily on the surfaces of diamond grains protected within their sturdy lattices. It's a tantalizing thought, quasars as accidental alchemists scattering the seeds of chemistry across the universe. Of course, not all that glitters is diamond. Some researchers argue these spectral signatures could come from other carbon structures, buckyballs, graphite, or even exotic forms like lonstellate, a theoretical carbon mineral harder than diamond. But whether they're true diamonds or cosmic imposters, one thing is clear. Quasars continue to defy expectations, turning even their dust into something extraordinary. The universe, it seems, has a flair for the dramatic, crafting jewels in the last place you'd ever think to look. At the heart of every quasar's brilliance lies a cosmic speed limit, the Eddington limit, a theoretical ceiling on how bright an object can shine before radiation pressure overwhelms gravity and blows away the very material fueling it. It's like trying to build a bonfire in a hurricane. Add too much wood and the wind snuffs it out. Yet scattered across the cosmos are quasars that mock this rule, blazing with intensities that should be impossible. Objects like S50014+813, whose luminosity exceeds its Eddington limit by a factor of 10. These cosmic rule breakers don't just bend physics, they snap it over their knee, forcing us to ask, are our models wrong, or is the universe playing by hidden rules? The Eddington limit isn't arbitrary, it's baked into the math of how black holes feed. When gas spirals into an accretion disk, the resulting radiation exerts outward pressure. At a certain brightness threshold, that pressure balances gravity's inward pull, creating equilibrium. Cross that line, and the radiation should repel incoming gas like a solar wind, starving the black hole. But super Eddington quasars laugh in the face of this balance, shining with the energy of hundreds of galaxies packed into a volume smaller than our solar system. One explanation: these quasars might be gorging on chaotic feasts rather than steady meals. Picture a black hole not sipping gas through a straw but gulping down entire stars or gas clouds in sporadic bursts. During these binges, the influx of material could temporarily swamp the radiation pressure, like a surging river overpowering a dam. Simulations show that in such cases, gas can plunge inward faster than the radiation can push it back, creating short-lived super Eddington flares. The quasar S0306++101, for instance, shows brightness spikes consistent with a black hole tearing apart sun-sized stars every few months, a gluttonous cycle of feast and famine. Then there's the geometry gambit. Traditional Eddington calculations assume spherical symmetry, a uniform shell of gas around the black hole. But what if the accretion disk is warped or clumpy? Magnetohydrodynamic models reveal that dense filaments of gas could channel material inward like cosmic tornadoes, slipping through gaps in the radiation barrier. Meanwhile, magnetic fields might corral the gas into narrow streams, shielding it from the brunt of the quasar's fury. It's the difference between trying to walk against a sandstorm versus navigating a shielded hallway. The destination's the same, but one path is far easier. The wild card in this puzzle is spin. A rapidly rotating black hole drags spacetime around it like a whirlpool, altering the dynamics of its accretion disk. Some theorists argue this frame dragging effect could effectively lower the local Eddington limit near the poles, allowing radiation to escape more efficiently while matter funnels in from the equator. In this scenario, a quasar could appear super Eddington from certain angles while obeying the rules locally, a cosmic sleight of hand tricking distant observers. But the most radical possibility, that super Eddington quasars are revealing flaws in our very definition of black hole physics. Alternative gravity theories, like those involving quantum corrections or extra dimensions, predict slight deviations from Einstein's equations under extreme conditions. If these quasars are pushing matter into regimes where general relativity starts to fray, their existence could be the first hint of new physics waiting to be uncovered. Observational clues are mounting. The James Webb Space Telescope recently spotted a quasar, J0348+0012, whose light spectrum suggests a photosphere of trapped radiation, a glowing surface where photons finally escape after countless collisions. This matches predictions for super Eddington flows where trapped light helps sustain the feeding frenzy. Meanwhile, the Event Horizon Telescope's next-generation targets include a super Eddington candidate, hoping to image its warped disk directly. What's at stake isn't just academic. If black holes can routinely violate Eddington limits, it rewrites the story of how they grew so massive so quickly in the early universe. It might also explain mysterious ultraluminous X-ray sources, cosmic objects that appear too bright for their size. Are they small black holes eating super Eddington or something even stranger? Every rule-breaking quasar is a crack in our understanding, and through those cracks we might just glimpse a universe far more audacious than we ever imagined. Among the most violent spectacles in the universe, few rival the raw power of a gamma-ray burst, an explosion so intense it can outshine entire galaxies in a single second. Now imagine that unfathomable energy packed into a relentless beam, aimed directly at Earth like a cosmic sniper rifle. This isn't just hypothetical, it's the reality of blazars, a special breed of quasars whose jets happen to point right at us, turning them into the universe's ultimate particle accelerators. Blazars are quasars with a deadly twist. While typical quasars shine in all directions, blazars channel their energy into narrow, high-speed jets of plasma that happen to be aligned with our line of sight. This alignment turns them into gamma-ray factories where particles are whipped to near light speeds by magnetic fields stronger than anything we could replicate on Earth. The result, a non-stop barrage of the highest energy photons in existence, including gamma rays capable of piercing through entire galaxies without breaking a sweat. The mechanics behind these gamma-ray jets are both brutal and precise. As material spirals into the black hole's accretion disk, some of it gets funneled into twin jets shooting from the poles. But unlike the messy outflows of regular quasars, blazar jets are streamlined by the black hole's spin and magnetic fields, creating a coherent beam. Particles within this beam, mostly electrons and protons, collide with photons and each other, generating gamma rays through processes with names like inverse Compton scattering and synchrotron radiation. The energies involved are staggering. A single blazar jet can produce gamma rays with 1 trillion times the energy of visible light. Some of these gamma ray bursts last mere milliseconds, while others flare for hours, but their impact is undeniable. In 2017, the blazar TXS 0506+056 made headlines when it unleashed a gamma-ray flare so powerful it briefly overshadowed all other sources in the sky combined. The event was detected by the Fermi Gamma-Ray Space Telescope, which watches the sky for such outbursts. What made this flare especially bizarre was its timing. Just days before, the same blazar had spat out a high-energy neutrino, a ghostly particle rarely caught in action. The coincidence suggested these jets might be cosmic multitaskers, capable of accelerating both photons and particles to extreme energies simultaneously. But here's the real kicker. Blazars might be responsible for some of the most mysterious signals in astrophysics: ultra-high-energy cosmic rays. These are protons and atomic nuclei hurtling through space with energies millions of times greater than anything our most powerful particle colliders can produce. For decades, their origins were a puzzle, but recent studies link them to blazar jets. The evidence, patterns in the arrival directions of these cosmic rays that seem to trace back to blazars like Markarian 501. If confirmed, it would mean these distant monsters aren't just lighting up the cosmos, they're bombarding it with subatomic bullets. Yet even blazars have their quirks. Some, like Bielacity, fluctuate wildly in brightness, dimming and flaring with no apparent rhythm. Others, like 3C279, show gamma-ray outbursts preceded by eerie quiet periods, as if the black hole is winding up for a punch. The most extreme cases exhibit superluminal motion, an illusion where jet material appears to move faster than light due to relativistic effects. It's a reminder that in the realm of blazars, the universe routinely defies common sense. What's next for blazar research? The Cherenkov telescope array, coming online in the next few years, promises to catch gamma rays with unprecedented precision, potentially revealing how particles reach such insane energies. Meanwhile, neutrino detectors like IceCube are on the hunt for more blazar-linked neutrinos, hoping to map the hidden pathways of these jets. Every new discovery peels back another layer of the blazar enigma, showing us that the universe's most energetic explosions aren't just random fireworks, they're targeted strikes, launched by black holes with terrifying aim. One moment a quasar is blazing across the cosmos, the next, its light winks out as if snuffed by an invisible hand. These abrupt disappearances, known as quasar eclipses, aren't the result of the black hole shutting down. Instead, they're cosmic hide and seek, vast clouds of gas or debris drifting into our line of sight, blocking the quasar's brilliance like a shadow passing over a spotlight. These events are more than just celestial curiosities, they're golden opportunities to map the chaotic neighborhoods around supermassive black holes, regions too turbulent and compact to observe directly. Take the case of Quasar J0152 plus 0015, which vanished for nearly 4 years before reigniting. Astronomers had front-row seats to the eclipse, watching as its broad emission lines, the fingerprints of gas swirling near the black hole, faded one by one. The culprit, a rogue dust cloud, likely flung outward by the quasar's own winds, dense enough to absorb nearly all visible light but thin enough to let some infrared radiation slip through. This spectral sleight of hand revealed something startling. The cloud wasn't a shapeless blob, but a structured filament, possibly a surviving fragment of a shredded star or a collapsing gas stream. Without the eclipse, we'd never have glimpsed this microscopic detail in a structure billions of light-years away. Even stranger are the quasars that dip in brightness predictably, like clockwork. One object, known as PDS 456, dims every 750 days, not from a single cloud, but from a whole squadron of them orbiting in a tight formation. This isn't random debris, it's a coordinated dance, hinting at a vast, clumpy disk of material circling far beyond the accretion disk itself. The regularity of these eclipses lets astronomers reconstruct the disk's architecture with astonishing precision, measuring the sizes, densities, and orbits of structures we'd otherwise never detect. It's like using shadows to trace the shape of an unseen object, only here. The object is a black hole's feeding ground, and the shadows stretch across the cosmos. Then there's the mystery of the disappearing broadline region. In some eclipses, not only does the quasar's continuum light fade, but the emission lines from its innermost gas clouds vanish too. This shouldn't happen. Those clouds are light-years closer to the black hole than any passing dust cloud could reach. The leading explanation, the eclipsing material isn't just blocking our view, it's absorbing the quasar's ultraviolet radiation, cutting off the energy that makes those gas clouds glow in the first place. It's like turning off a blacklight in a fluorescent room. The paint doesn't disappear, but its brilliance does. These events act as natural experiments, letting astronomers test how quasars illuminate their surroundings in real time. The most extreme eclipses, however, defy all expectations. In 2018, quasar J0234-0780 dropped in brightness by a factor of 50 in just 2 years, far too fast for any known cloud to move across its face. Some researchers suspect this wasn't a cloud at all, but a sudden avalanche of dust collapsing inward, triggered by a disturbance in the quasar's dusty torus. Others propose something wilder, a warp in the accretion disk itself, tilting to block our view like a tilted vinyl record catching the light. If confirmed, it would mean quasars can reshape their own visibility without any external help. What makes these eclipses invaluable is their forensic detail. By measuring how different wavelengths dim X-rays first, then ultraviolet, then visible light, astronomers reconstruct the eclipsing material's composition. Some clouds are rich in graphite, others in silicates. Some are as hot as molten iron, others cold enough to harbor frozen carbon monoxide. Each eclipse is a snapshot of the quasar's feeding process, catching it in the act of devouring, or expelling the very stuff that fuels its fury. But the grand prize would be catching an eclipse caused by a single, star-sized object, perhaps a planet spiraling into the black hole or a stellar corpse on a doomed orbit. The light curve would be unlike anything seen before, a sharp dip with subtle ripples encoding the object's size, speed, and even atmospheric composition. It's a long shot, but with next-generation telescopes like the Vera Rubin Observatory scanning millions of quasars nightly, the odds improve. Every flicker, every dimming is a message in a bottle, a scrap of data flung across space-time waiting to be decoded. Quasars don't just shine, they feast, and some of the universe's most violent banquets happen when galaxies collide, ripping apart stars and funneling rivers of gas straight into the maw of a supermassive black hole. These cosmic smash-ups are galactic cannibalism on the grandest scale, where entire galaxies become fuel for the brightest objects in existence. The evidence is written in the twisted wreckage of quasar-host galaxies, spirals stretched into grotesque shapes, elliptical galaxies with tails of stolen stars, and mergers so chaotic they look like abstract art painted in starlight. Take the case of NGC 6240, a galaxy that resembles a celestial Rorschach test. Its twin nuclei, each harboring a supermassive black hole, are locked in a death spiral, separated by just 3,000 light-years. Surrounding them is a maelstrom of gas, violently stirred by gravitational tides. Infrared telescopes reveal this gas glowing hot, funneled into the black hole's accretion disks like water swirling down a drain. The result, a double quasar, its light echoing across the cosmos as the galaxy's dance of destruction plays out in slow motion. This is no quiet merger, it's a fireworks display of star formation and annihilation, all set against the backdrop of a black hole's feast. But what makes these collisions such perfect quasar fuel? The answer lies in angular momentum, or rather, the lack of it. In a stable galaxy, gas orbits peacefully, its motion preventing it from falling directly into the central black hole. But during a merger, gravity tangles everything. Gas clouds slam into each other, cancelling out their momentum and sending material plummeting inward. Simulations show that these collisions can dump thousands of suns worth of gas into the galactic center within a few million years. Enough to ignite a quasar that outshines the combined light of every star in both galaxies. Some of the most dramatic examples come from ultra-luminous infrared galaxies, or ULERG objects so shrouded in dust they glow faintly in visible light but blaze like cosmic furnaces in infrared. Many of these systems, like ARP 220, are caught mid-collision, their distorted shapes betraying recent gravitational violence. Dig deeper into their spectra, though, and you'll find the telltale signatures of quasars buried within. The dust is a giveaway. It's the smokescreen of a feeding frenzy, hiding the brilliant accretion disk as it devours merger-flung gas. Not all galactic collisions spawn quasars, though. The key seems to be the gas reserves of the merging galaxies. 2 gas-rich spirals, recipe for a quasar. 2 gas-poor ellipticals, a quiet merger with little fanfare. The quasar H0421 plus 0624 illustrates this perfectly. Its host galaxy shows tidal tails, streamers of stars flung outward by a past collision, yet the quasar itself is oddly dim. The likely explanation: the merger involved galaxies already starved of fuel, leaving the black hole with nothing to gorge on. It's a cosmic irony. The violence was there, but the pantry was bare. The aftermath of these feasts can be just as revealing. Quasar host galaxies often show post-starburst spectra signatures of a recent, rapid burst of star formation followed by abrupt quenching. This makes sense. The same collision that feeds the black hole also compresses gas to form new stars, but the quasar's eventual outburst blows away the remaining fuel, halting further stellar births. It's a boom and bust cycle written in starlight, with the quasar playing the role of both creator and destroyer. The most unsettling implication: our own Milky Way is on a collision course with Andromeda, due to merge in about 5 billion years. Will the resulting chaos ignite our now dormant supermassive black hole into a quasar? Possibly, but by then, the universe's star-forming gas will be so depleted that the feast might be meager. Still, it's a humbling thought. The same forces that light up quasars across the cosmos are part of our galaxy's inevitable future. The universe doesn't just create, it consumes, recycles, and reinvents, with quasars as the brilliant flashpoints of its endless transformation. Measuring the universe is one of astrophysics' greatest challenges. How do you gauge distances to objects so far away that their light has traveled for billions of years before reaching us? For decades, astronomers have relied on standard candles, objects with known intrinsic brightness like Type 1a supernova, to map cosmic expansion. But what if quasars, the universe's most chaotic objects, could serve as the next generation of distance markers? The idea is as tantalizing as it is controversial, pitting cutting-edge statistical methods against the fundamental unpredictability of these cosmic monsters. At first glance, quasars seem like the worst possible rulers. Their brightness fluctuates wildly, their accretion disks vary in size and composition, and no 2 quasars look exactly alike. Yet beneath this chaos, patterns emerge. In 2013, astronomers noticed something peculiar: the time it takes for a quasar's accretion disk to respond to brightness changes. A delay called the lag luminosity relation appears to correlate with its intrinsic brightness. Picture shouting into a canyon. The time it takes for the echo to return depends on the canyon's size. Similarly, larger, brighter quasars have thicker accretion disks, creating longer lags between ultraviolet and optical light variations. This discovery opened the door to using quasars as potential cosmic yardsticks. The method hinges on reverberation, mapping a technique that measures how light ripples through a quasar's inner regions. By tracking delays between fluctuations in different wavelengths, astronomers can estimate the physical size of the accretion disk. Combine that with the observed brightness, and you theoretically have a distance indicator. The potential is enormous. Quasars are visible across 90% of the universe's history, far beyond the reach of most supernovae. They could let us measure cosmic expansion during the mysterious dark ages before stars formed, if only the method were precise enough. But here's the catch: quasar variability is messy. Magnetic instabilities, clumpy gas flows, and even secondary black holes can distort the lag luminosity relation. Some quasars defy the pattern entirely, like J0318-0721, whose lag times bounce erratically despite stable luminosity. Critics argue that without understanding what drives these outliers, quasar distance measurements risk systematic errors that could skew our entire cosmic map. Imagine building a house with a rubber tape measure. Every measurement might stretch unpredictably. Supporters counter with brute force statistics. By analyzing tens of thousands of quasars, machine learning algorithms can identify subtle correlations invisible to human observers. The Sloan Digital Sky Survey's Quasar Catalog, for instance, reveals that while individual quasars are erratic, their collective behavior follows predictable trends. It's like forecasting weather. You can't predict a single raindrop's path, but you can model a storm system with startling accuracy. Recent studies using this approach have measured the Hubble constant, the rate of cosmic expansion, to within 5% of supernova-derived values, a promising start. The stakes couldn't be higher. Current distance methods disagree on the universe's expansion rate, a crisis dubbed the Hubble tension. Quasars, observable across vastly different epochs, might settle the debate by revealing whether the tension stems from measurement errors or new physics. Some theories, like evolving dark energy, predict divergence in expansion rates that only quasars could detect across their full chronological range. Yet even optimists admit hurdles remain. Dust in intervening galaxies can dim quasar light unpredictably, while relativistic beaming, where jet orientation artificially amplifies brightness, adds another layer of distortion. The James Webb Space Telescope offers hope, peering through dust with infrared eyes and resolving quasar structures once blurred by distance. Meanwhile, upcoming surveys like the Vera Rubin Observatory will monitor millions of quasars nightly, building datasets vast enough to filter out noise. The Dream, a three-dimensional map of the universe with quasars as mileposts stretching back to the first billion years after the Big Bang. It's a gamble, but in cosmology, fortune favors the bold. If perfected, Quasar standard candles wouldn't just measure space, they'd rewrite the timeline of cosmic evolution itself. Quasars are supposed to be the ultimate cosmic show-offs, blazing at the hearts of massive, chaotic galaxies where endless streams of gas and stars feed their monstrous black holes. But the universe loves breaking its own rules. Scattered across the void are renegade quasars shining from the most unlikely places imaginable. Picture a single fiery street lamp in an empty desert. That's what it's like to find a quasar glowing in a red and dead galaxy. A quiet retirement home for aging stars where nothing should be able to spark such violence. Or consider He 1328 plus 0627, a quasar burning defiantly in a near-empty region of space, its host galaxy so faint it's practically invisible. These misfits shouldn't exist, and yet they're rewriting the story of how black holes grow. The puzzle starts with fuel. Quasars need a staggering amount of material, entire stars' worth of gas every year, to sustain their brilliance. In bustling galaxies, frequent collisions and dense gas clouds keep the black hole's pantry stocked. But in isolated or quiescent galaxies, the menu is sparse. So how do these outliers keep shining? One clue comes from their host galaxy's subtle scars, faint tidal tails or distorted shapes hinting at ancient mergers. Even quiet galaxies might have turbulent pasts. A single violent collision billions of years ago could have dumped enough gas into the central black hole to ignite a quasar that lingers long after the galaxy's star-forming fires burned out. It's like finding a still-burning ember in a cold fireplace, evidence of a feast that ended eons ago. Then there's the enigma of black hole seeding. Traditional models assume supermassive black holes grow gradually, starting from the collapsed cores of massive stars. But some rogue quasars, particularly those in the early universe, are too massive too soon. Take J0348 plus 0012, a quasar shining just 670 million years after the Big Bang, yet weighing in at nearly 1 billion solar masses. Even if it ate non-stop at the theoretical maximum rate, there's not enough time for a stellar mass black hole to grow that large. The answer might lie in direct collapse black holes, hypothetical monsters born not from stars but from the instantaneous collapse of primordial gas clouds. These titans could have emerged fully grown, skipping the stellar phase entirely, and quasars in unexpected places might be their descendants. The plot thickens with quasars like J1148 plus 5255, which defies expectations by residing in a galaxy with unusually low dust levels. Dust is typically a byproduct of rampant star formation, so its absence suggests this black hole found a way to feast without triggering the usual stellar fireworks. One radical theory proposes that in these sparse environments, black holes might siphon gas directly from the cosmic web, the vast, invisible filaments of hydrogen threading the universe, bypassing the need for galactic drama altogether. What do these oddballs teach us? First, that supermassive black holes are far more resourceful and opportunistic than we imagined. They don't need a galaxy's constant chaos to thrive. Sometimes a single ancient feast or a stealthy cosmic tap is enough. Second, their existence hints at a hidden diversity in black hole origins. The universe might have forged these giants through multiple paths, some via stellar corpses, others as primordial behemoths birthed in the collapse of pristine gas. Most intriguingly, these outliers could be the key to a long-standing mystery: why nearly every massive galaxy, even the quiet ones, hosts a central black hole. If black holes can grow in isolation or emerge fully formed, it would explain how they became universal fixtures rather than rare anomalies. The cosmos, it seems, has more than one way to build a monster, and quasars in unexpected places are the clues we're just beginning to decode. The universe's brightest lights won't shine forever. As galaxies drift farther apart in our expanding cosmos, the rivers of gas that feed quasars will slowly dry up, leaving their supermassive black holes to starve in darkness. Imagine a cosmic metropolis where the power grids flicker out one by one. First, the most distant quasars, those blazing in the early universe, will exhaust their fuel as their host galaxies grow barren. Then, over tens of billions of years, even the nearest quasars will dim, their accretion disks evaporating like morning dew. The era of quasars, this breathtaking chapter where black holes turned matter into light with terrifying efficiency, will fade into a quieter, colder epoch. Yet the Milky Way's own sleeping giant, Sagittarius, a star, might have one last act. Right now, it's a placid beast barely nibbling on wisps of gas. But the future holds a cataclysmic reunion, our galaxy's impending collision with Andromeda in about 5 billion years. When these two spirals merge, their chaotic dance could funnel vast reservoirs of gas toward their central black holes. For a brief, spectacular moment, Sagittarius, a star, might awaken as a quasar, outshining every star in the newborn Andromeda galaxy. Simulations suggest this fiery rebirth could last millions of years, bathing our galactic neighborhood in radiation intense enough to sterilize any surviving planets. But this late-stage quasar would be a swan song. As the merged galaxy ages and its gas supply dwindles, Sagittarius, a star, will return to slumber, joining the ranks of relic black holes scattered across the universe. These dormant giants will still lurk in galactic centers, but without fresh fuel, they'll emit only faint whispers of Hawking radiation, a quantum mechanical glow so feeble it's practically undetectable. The universe's once vibrant quasar population will become a graveyard of dark titans, their brilliant past preserved only in the redshifted light traveling eternally through the void. There's a haunting beauty to this distant future. The last quasars will vanish long before the universe's final stars flicker out, marking the end of an era defined by violent brilliance. What comes next is a cosmos of deepening shadows where black holes, having feasted on galaxies, are left with only echoes of their former glory. Yet even in darkness, they'll shape the universe's fate, their gravity anchoring the skeletal remains of galaxies as expansion pulls everything farther apart. The Milky Way's quasar phase, if it comes, will be brief, but it's a reminder that even our quiet corner of space isn't immune to the universe's cycles of destruction and rebirth. One day, long after Earth is gone, our black hole too may blaze again, a final flash of light in the endless night. From their mind-bending super-Eddington brilliance to the eerie alignment of their spin axes across billions of light years, quasars have proven to be the universe's ultimate rule breakers. We've explored how these cosmic monsters flicker like dying light bulbs despite their colossal size, how their diamond-studded outflows scatter stardust across galaxies, and how their gravitational mirages warp space-time into celestial funhouse mirrors. We've witnessed orphan quasars floating untethered in the void, binary quasars locked in slow-motion duels, and zombie quasars that resurrect from dormancy to unleash fresh cataclysms. Every discovery peels back another layer of mystery, revealing how these objects sculpt galaxies with their hurricane-force winds, imprint chemical fingerprints on the early universe, and even potentially seed the cosmos with the building blocks of life. Yet for all we've uncovered, quasars remain cosmic riddles wrapped in enigmas. Why do some flicker with clockwork precision while others rage unpredictably? How can their spin axes possibly align across unimaginable distances? And what unknown physics allows a handful to shatter the Eddington limit, blazing brighter than the laws of thermodynamics should allow? Each answer begets new questions, proving that the more we study these luminous beasts, the less we truly understand. As our telescopes grow sharper and our simulations more sophisticated, one thing is certain: quasars still hold secrets that could rewrite astrophysics. Will we find evidence of primordial black holes born from the Big Bang itself? Could their jets reveal hidden dimensions or new states of matter? And if dark matter truly puppeteers their spins, what other cosmic strings might it be pulling behind the scenes? The universe has a habit of defying our expectations, and quasars, with their defiant brilliance, remind us that the most profound discoveries often lie just beyond the edge of our current understanding. So tell us in the comments which quasar phenomenon left you awestruck: the diamond rain, the ghostly light echoes, or the spine-tingling possibility that these objects might be threading the universe with invisible dark matter filaments. The cosmos is stranger than fiction, and every time we gaze into a quasar's heart, we're staring into the unknown. Don't forget to subscribe and hit that notification bell, because the next cosmic revelation could be just one telescope scan away.